Okay, now the sample's wet and hopefully not glary. Okay, so here's the really strong through-going planes that segment the oblique fabric. Those through-going planes are the cisellement. The C planes, or shear planes, that cut across and make a very high strain zone that's at an acute angle to these intermittent ones that bound the sigma clasts. So I hope you're anticipating what is the name for the short intermittent fabric. The intermittent one is the S fabric, the schistosity. Okay, so which one of these is perpendicular to Z? This stands for shear. I think you will remember by analogy with brittle faults. The shear plane is not the one that experiences the maximum normal stress, rather it's at some angle to it. So Z, by analogy with what you've learned about brittle faults, the Z, or shortening axis, imposes too much shortening in that orientation. So not C, that's not the one to look at, but rather, to fix the orientation of Z, it's the intermittent schistosity, the S fabric. So we'd fix the Z direction of the strain ellipsoid in this motion plane view, perpendicular to S, and the x-axis of stretching parallel to that plane and parallel to lineation. Parallel to Z plane and fixed in space by the L fabric. Okay, now what about interpretation of shear sense? This geometry creates, and we could generalize each of these lozenges. Here I'm going to point to this potassium feldspar and draw it into this diagram. We can view that as a sigma clast with an asymmetry, and we could generalize that as a symmetrical shape that's useful, and that's a strain ellipse, a reference ellipse that's long axis goes with X, short axis goes with Z. We can picture an angle of inclination of ellipses that fill these rhomboid spaces. The inclination of the ellipse points in the direction of shear. As a cross check on this, the sigma class tails, top tails, point in the direction of shear. This sample, as held in my hand, is recording a kinematic shear sense of top to the left, top to the left. Now I'm going to finish with a look at just one more sample, and fair warning, photo images of these three myelinitic LS tectonites, one of them with a bookshelf feldspar, are going to be provided to you to mark up in this way. The final sample that I want to show is one from Colorado that offers an internal marker. These are quartz sillimanite pods that we interpret originated as spheres They've now been deformed into the shape of ellipses like those. They can be used as a geometrical reference for quantifying the amount of strain, how much flattening in respect to Z, how much, can I see the angle you're showing? Yeah, can you just go like this? Great. Okay. How much flattening with respect to Z, how much stretching parallel to S is responsible for making this shape, which is comparatively low strain. This is cut along the motion plane. It can be also interesting to look at an orthogonal plane. This is the YZ plane. This is the XZ plane for a rock that contains once spherical markers, now deformed into ellipsoids, that we can use to make comparisons. It's like drawing one of these out and having a shape like this, that it can use X, Y, Z dimensions, to get measures of the amount of deformation that this rock experienced, all the while maintaining continuity without breaking.